Electric field and important aspects of electric field. Welcome to Physics for Everyone. Let us first learn about electric field. Next, let us learn about important aspects of electric field. Michael Faraday, action at a distance. How does the second charge know about existence of the first charge which is located at some distance away from it? To answer this question, Michael Faraday introduced the concept of field. According to Faraday, every charge in the universe creates an electric field in the surrounding space, and if another charge is brought into its field, it will interact with the electric field at that point and will experience a force. According to Faraday, every charge in the universe creates an electric field in the surrounding space, and if another charge is brought into the field, it will interact with the electric field at that point and will experience a force. The field concept is required to explain the action at a distance. Here you have a positive charge and gives out the electric field radially away from it. This is called source charge. The charge plus Q which produces the electric field is called source charge plus Q0. It's another infinitesimally very small charge. We call it as test charge. The charge plus Q0 which experiences the effect of source charge is called the test charge. Electric field intensity. There are two charges plus Q and plus Q naught placed at some distance away from each other. The plus Q naught experiences a force due to plus Q, F vector. The electric field intensity at any point due to a source charge is defined as the force experienced per unit positive test charge placed at that point without disturbing the source charge. So, F vector by Q naught gives the electrical field intensity E vector, which is equal to the force divided by unit positive test charge, where E equals the electrical field intensity and F equals force experienced by the test charge. It is a vector quantity and its SI unit is Newton Coulomb inverse. The dimensional formula of electrical field intensity is force per charge, mLT power minus divided by AT equals mLT power minus 3 A power minus 1 is the dimensional formula of electrical field intensity. Here you have the plus Q charge which is greater than 0. For a positive charge, the electric field vector is directed radially outwards, that is away from the positive charge. Here you have a minus Q negative charge. The electric field now towards the negative charge. Q is less than 0. For a negative charge, the electric field vector is directed radially inwards, that is towards the negative charge. Electric field due to a point charge. Here you have a xy coordinate. To find the electric field at a point P at a distance r from the source charge Q, we have to find the electric force on a test charge Q naught placed at point P. At the origin, you have the source charge plus Q. Now at a distance r, you have a test charge Q naught. According to Coulomb's law, force on the test charge Q0 due to the charge Q is given by F vector. F vector equals 1 by 4 pi epsilon naught Q naught by R square R cap. Now we know E vector equals force vector divided by Q naught, the test charge. And remember that this Q naught must not disturb the electric field produced by the source charge. So it must be very small. So E vector equals limit Q naught towards 0 F vector by Q naught. Right? So let us know this, but let us avoid this in our right now calculation. So let us substitute the F in this equation, and we find that Q naught in the E equation and F equation cancels. So we get E vector equals 1 by 4 pi epsilon naught Q by R square R cap. The magnitude of the electric field at a point P is E equals 1 by 4 pi epsilon naught Q by R square. Important aspects of electric field. The same diagram. E vector equals K times Q divided by R square R cap. The unit is Newton per Coulomb. E vector is the electric field, K is the Coulomb's constant, Q is the source charge, R square is the square of the distance between the source charge and the test charge, point charge, point. R vector is the unit vector, and Newton per Coulomb is the unit of, SI unit of electric field. The first aspect. The electric field at any point in space due to the charge depends only on the distance. That means the magnitude of the electric field due to a point charge is same at all points of the sphere. That is, it has spherical symmetry. Now, what is the direction of electric field at point P? If the charge Q, the source charge Q is positive, the electric field points radially away from the source charge plus Q. If the source charge is minus Q, then the electric field direction is towards minus Q, negative charge. If Q is negative, the electric field points radially towards the source charge minus Q. Now, what is the direction of force experienced by Q naught? It is shown in the diagram for plus Q and minus Q. Let us first do it for plus Q. F vector equals Q naught times E vector. It is another formula of Coulomb's law. For negative charge, direction of force is towards the negative charge. F vector equals Q naught E vector. If the electric field at a point P is E vector, then the force experienced by the test charge Q naught placed at that point P is F vector equals Q naught times E vector. This is the Coulomb's law in terms of electric field. Plus Q vector, and it's a point P, right? Then the electric field will be away from the line joining the two charges, away from the source charge. The electric field at P is represented by EP vector. Let us have another point Q. The direction of electric field at Q is given by EQ vector, and another point R. The electrical field direction is given by ER vector. Look at the point PQR, right? The P is well away, the R is well close to the source charge. Look at the length of each vector, right? The ER vector, the length of the ER vector is larger than the length of the EQ vector, which is larger than the length of the EP vector. That means as the distance increases, the magnitude of the electric field decreases. Here for negative charge, we have 3 points P, Q and R. Now these electric field directions are all towards the negative charge. Look at the length of each vector, ER vector. The length of the ER vector is more than the length of the EQ vector, which is more than the length of the EP vector, because when the distance increases, the magnitude of the electrical field intensity decreases. Since the electric field is a vector quantity. At every point in space, this field has a unique direction and magnitude as shown in the figure. E vector equals 1 by 4 pi epsilon naught q by r square. As the distance increases, the electrical field decreases in magnitude. So the length of the vector becomes lesser and lesser as we go away from the source charge. This is a source charge plus q naught is the test charge. E vector equals limit q naught tends to 0 f vector by q naught. The test charge is made sufficiently small such that it will not modify the electric field of the source charge. Types of electric field. There are two kinds of electric fields. Uniform electric field. Uniform electric field will have the same direction and constant magnitude at all points in space. Look at the diagram. The length of each vector are equal and the directions are same. So this diagram represents uniform electric field. Non-uniform electric field. Non-uniform electric field will have different directions or different magnitudes or both at different points in space. As we go towards right, the magnitude of this electric field decreases, but they have same direction but different magnitude. So it's a non-uniform electric field. In this diagram, the length of each vectors is same, but the directions are different. It's also called a non-uniform electric field. Here it's a converging electric field. It's a non-uniform electric field. If Q is positive, Q is greater than 0, then you have an electric field that is directed radially away from the source charge. If it's a negative charge, then the electric field directed towards the negative charge. The electric field produced by a point charge is a non-uniform electric field. The direction of electric field is radially outward or inward, and the magnitude of the charge as distance increases. The magnitude of the charge decreases as the distance increases. There is a little error over here in my typing. Magnitude of the resultant of two electric fields E1 vector and E2 vector, Q1 and Q2, they produces a resultant electric field at a point P. At point P, the electric field due to Q1 is, we call it as E1 vector. The electric field at P due to Q2 vector, we call it as E2 vector. Right? It's separated by an angle theta. Now to find the resultant electric field, we use triangle of vector addition. Taking E1, E2 are the adjacent side of a triangle and the closing side taken in the opposite order is the resultant. It's called E net vector, which makes an angle alpha with the E1. So E net vector equals E1 vector plus E2 vector. Magnitude of the E net vector equals root of E1 square plus E2 square plus 2 E1 E2 cos theta. Tan alpha equals E2 sin theta divided by E1 plus E2 cos theta. Superposition of electric fields due to discrete distribution of charges. The electric field at a point due to a collection of point charges is equal to the vector sum of the electric fields created by the individual point charges. So we can say that E vector equals E1 vector plus E2 vector plus dot 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 up to En vector. So E net vector equals summation of I starts from 1 to n Ei vector. Superposition of electric fields due to continuous distribution of charge. For continuous and finite size charge distributions, integration techniques must be used. E vector equals 1 by 4 pi epsilon naught integration dq by r square r cap. Linear charge distribution dq equals lambda dl. Surface charge distribution dq equals sigma dA. Volume charge distribution dq equals rho dV. Let us learn about lambda, sigma, rho in the next page. Sir, superposition of electric fields due to continuous charge distribution. Linear charge distribution. Charge distributed on a line. Charge on a wire or ring. Here you have a wire. It has a charge Q and it has a length L. Linear charge density lambda equals Q by L. Let us take a small element. The charge in the small element dq equals lambda dl. Let us consider a point P at a distance r as a unit vector r vector. The electric field at point P E vector equals 1 by 4 pi epsilon naught integration dq by r square r cap. Let us replace dq by lambda dl. So the final equation E vector equals lambda by 4 pi epsilon naught integration dl by r square. For a ring, lambda equals q by 2 pi r. The length is replaced by the circumference. Unit of linear charge density is Coulomb meter inverse. Surface charge distribution. Charge distributed on a surface. Charge on a conducting sphere or sheet. For a conducting sphere, the charge never available inside the sphere, only available on the surface of the sphere. Here you have a sheet, has a charge Q and an area A. Surface charge density sigma equals Q by A. The charge per unit area. Let us consider a small element has a charge dq equals sigma dA. Same way, a point is being considered. Let us find the electric field at point P. E vector equals 1 by 4 pi epsilon naught integration dq divided by r square r cap. Now let us replace dq by sigma dA. And the final equation is E vector equals sigma by 4 pi epsilon naught integration dA divided by r square r cap. For a sphere, sigma equals q by 4 pi r square. The surface area of a sphere is 4 pi r square. The unit of sigma is Coulomb meter power minus 2. Volume charge distribution. Charge distributed over a volume. Charge on a non-conducting sphere. Charges are localized in the higher locations. A non-conducting cube is taken, has a charge Q and a volume V. Volume charge density rho equals Q by V. It is not A here, it is V. It is V, sorry. So dq equals rho dV. Let us find the electric field at point P. E vector equals 1 by 4 pi epsilon naught integration dq by r square r cap. Let us replace dq by rho dV. And we have the final formula E vector equals rho divided by 4 pi epsilon naught integration dV by r square r cap. For a non-conducting sphere, rho equals q by 4 by 3 pi r cube. The unit of rho is coulomb meter power minus 3. Thank you, children.